Hello, my name is Faiz, and today I will be presenting Conformal Off-Policy Prediction in Contextual Bandits. This is a joint work with Jean-Francois, Rob Cornish, E.Y. Tay, and Arnaud Duché. We will start with the setup of our problem. Consider the example of a recommendation system. Here X represents the users, A represents the action that is taken, in this case the item that is recommended to the user, and Y represents the outcome, that is whether the item is relevant to the user or not. In our setup, we have access to some log data, X, A, and Y, which was collected using a possibly unknown behavioral policy. We call this PyB. In our example, the policy could be an old recommendation system that has already been implemented in the real world. Our goal is as follows. For a new target policy, which we call Pi star, and a user X, we would like to find the set of probable outcomes for X if the actions are chosen according to the new target policy. One way to achieve this goal is to construct an interval or set C hat of X with the following three properties. Firstly, the set should be adaptive with respect to X, which means that in our case, the sets should be dependent on the users. Secondly, the set should capture the variability in the outcomes Y. And thirdly, we should have theoretical guarantees for the constructed set C of X. To be more concrete, the theoretical guarantees that we seek are shown in the equation. What this says is that the set C hat of X captures the true outcome Y with a user pre-specified probability threshold, in this case 1 minus alpha. Note that the upper bound to the coverage guarantee ensures that the sets obtained are not too conservative. In this case, the probability is taken over the joint distribution of X and Y under the target policy and not the behavioral policy. Here's a quick comparison of our methodology with traditional off-policy evaluation methods. Most works in the off-policy evaluation literature do not account for the variability in the outcome, but are rather interested in the expectation. And secondly, existing methods are not adaptive with respect to X. This becomes more important in risk-sensitive settings where some measure of uncertainty is important. In comparison, our method, COP, is able to provide a granular information about individualized performance of policy for each user, as well as the uncertainty in the outcome. To achieve this goal, we use conformal prediction and apply it to contextual bandits. Here we provide a brief high-level background. Conformal prediction is a distribution-free uncertainty quantification method which allows us to output set-valued predictions instead of outputting point predictions. The standard conformal prediction requires that the training and the testing data should be exchangeable. Under this assumption, we are able to construct sets C of X with the guarantees shown on this slide. This means that for a new point X, the set C of X will capture the true outcome with a user-specified probability. However, the assumption of exchangeability can be easily violated due to distributional shift. Take the example of covariate shift. In this case, the conformal prediction would not be applicable anymore, and therefore the guarantees would be void. For this problem, Tipshirani et al. Proposed a different notion of exchangeability, called weighted exchangeability. Similar to most covariate shift problem, estimation of the density ratio is crucial, and this is no exception. Tipshirani et al. Show that if one is able to properly estimate the weights, W of X, one can in fact obtain similar statistical coverage guarantees as in standard conformal prediction. Coming back to our problem of off-policy prediction, recall that in our setting, we have calibration data from behavioral policy, but the test data comes from a different target policy. The main idea of our methodology is to consider the following decomposition of the joint distributions. The joint distribution of xy can be decomposed into the covariate distribution of x and the conditional distribution of y given x. These equations show that a shift in the policy leads to a shift in the conditional distribution of y given x, whereas the covariate distribution remains constant. Therefore, adapting ideas from Tipshirani et al., one can in fact still perform valid conformal prediction in the off-policy setting if we have access to the density ratios. For exact details and theoretical results on how we construct the conformal intervals, please see our paper. We would like to also illustrate some real-world data experiments that we ran on Microsoft ranking dataset. Our dataset consists of 10,000 users for which we recommend websites. The user-website pair is then subsequently assigned a relevance score. The goal in this task is to find the set of most probable outcomes for a user X under a new unseen target policy pi star. Here we present the results from our experiments. The table shows the coverage of sets constructed using our methodology COP compared against other baselines as the policy shift between the behavioral policy and the target policy increases. Note that the required coverage for this experiment is 90%. It can be seen that our methodology provides near to perfect required coverage for all target policies, even with increasing policy shift. On the other hand, the sets obtained using other methodologies are too conservative. Lastly, we present some interesting avenues for future work. Conditional coverage guarantees that we have in our paper currently rely on strong assumptions. An interesting question for future would be to weaken these assumptions. Furthermore, we think that it would be an interesting addition to extend this to sequential decision-making problems with evolving policies. And lastly, applying COP to robust policy learning is an interesting avenue of work as well, as it would allow policy optimization by optimizing the worst case outcome. Thank you for listening, and please check out our paper if you're interested for more details.